This video is a little different from what I normally do. I normally work on concrete mathematical problems, and I take those problems and solve them and abstract some particular mathematical principle or idea from them. Here at the moment in New Zealand, we're in the middle of a level 4 lockdown, so there's plenty of time to consider or muse over things at the moment. It's the second time, incidentally, that this has happened here. This level 4 lockdown is due to cases of the Delta variant of COVID-19 which have emerged in the community. My musings here in this video are really influenced by listening to multiple other experts or authorities who have touched on this avenue of inquiry, and it's about essentially the cosmos and potentially the spread of life out there that we haven't already come across. What we're looking at here is a picture of Messier 101, the Pinwheel Galaxy, and this has been captured by the Hubble telescope and Earth-based telescopes. It's a composite image that has been stitched together from multiple images, from over 50 images over several years. Messier is similar in appearance to our galaxy. It's 170,000 light years across. As I said, similar but a little larger than the Milky Way. The best estimate for the number of stars here is 1 trillion. That's a 1 followed by 12 zeros, or 1,000 billion, or a million millions. 1 trillion. It's 25 million light years from Earth, so that the light that we've seen from it, from which this image has been captured, left the system 25 million years ago. So it shows us what the system looked like 25 million years ago. That light, when it left this galaxy, at that time Earth was 25 million years younger than it is now. So even the earliest descendants of man hadn't appeared on Earth. So what we see on the screen here is a series of figures which represent an experiment which we're going to carry out, which will be demonstrated following a mathematical idea. What we're looking at really is the potential for life within this galaxy. So first of all, we're going to limit ourselves to the Milky Way rather than to everything beyond that. And the second thing we're going to assume is that life is present only on planetary systems. Humanity lives on Earth, which is within a planetary system. We're going to assume all other life lives only on planetary systems. For all we know, it could be on satellites, on moons, and Oort clouds, or within any other number of phenomena within the galaxy, but we'll assume only planetary systems. Now, the size of our galaxy is 100,000 light years in diameter. That means traveling at the speed of light, which is 3 times 10 to the 8 meters per second, 300,000 kilometers per second, which is the upper limit, hypothetically, that anything can travel at within our universe. It would take 100,000 years to go from one side of the galaxy to the other. And the best estimate for the number of stars within our galaxy is 100 billion. As a lower end estimate. That's 100 followed by 9 zeros, or a 1 followed by 11 zeros. I'm going to scale that up to the upper end of that estimate, say 400 billion, so that we can assume that there are more stars than there really may be in our galaxy. And the next important assumption I'm going to make is about the distances between any two stars within our galaxy. Now, as I've just talked about, our galaxy is 100,000 light years in diameter. That means the furthest any two stars could be from each other within the Milky Way is 100,000 light years apart. I'm going to assume any two stars that are picked at random are 100,000 light years apart, when the vast majority are far closer than that. The reason for that will become apparent soon enough. That's the setup for this thought experiment. Now, what we're looking at on screen represents a machine or a robot that we want to build that's designed to populate every star system within the Milky Way. We build one machine, and it's sent from Earth to the nearest star, remembering that all stars in the sky are equally far away from each other, 100,000 light years. Once this robot machine arrives at that star, it stays there, but it creates two replicas, and the two replicas leave to populate two other star systems, and they then follow the same course. They stay on those respective star systems, and each creates two more replicas. So 4 replicas are then generated to go out and populate 4 more star systems, and so on. And hence, we have the numbers doubling line by line as we go down the page, from 1 to 2 to 4 to 8 to 16, and so on. So, what we have here is an exponential growth function, and it's modeled by the following. Y is equal to a to the power of x, where a is what's called the base and x is the exponent. In this case, a is 2, which is a very low value, but still, even with this low value, this curve grows very rapidly. So the formula for the number of figures on each row is given by 2 to the power of x minus 1. So on the first row we have one figure. The first row becomes 2 to the power of 1 minus 1, 2 to the power of 0 equals 1. One figure on the first row. On the second row we have 2 figures, so the formula for that number is given by 2 to the power of 2 minus 1, which is 2 to the power of 1, which is equal to 2, and so on. Now, before I continue, if you maximize this video so it plays full screen on your laptop, you'll be able to see that the distance between the left and right figures on line 2, where there are 2 figures only, is about 20 centimeters. It's a little bit less than that, but say it's 20 centimeters. If I had kept that distance constant as we moved down the page, which I couldn't do because I was cramming more figures into each line, but if I had kept that distance constant, then by the time we got down to the 8th line, where there is 2 to the power of 7, which is 128 figures jammed together, then those figures, the distance from the leftmost figure to the rightmost figure would be 25 meters. By the time we go 7 lines below that to the 15th line, the distance from the leftmost figure to the rightmost figure would be 3,276 meters. By the time we go 5 lines below that to the 20th line, the same distance would be 105 kilometers. By the time we go 10 lines beneath that to the 30th line, the distance from the leftmost figure to the rightmost figure would now be 215,000 kilometers, which is more than half the distance from the Earth to the Moon. 10 lines below that to the 40th line, the distance from the leftmost figure to the rightmost figure would now be 215 million kilometers, which is about a third more of the distance than from the Earth to the Sun. So the point here is that these numbers rapidly increase. Let's look at those numbers again briefly. That first number that we looked at was 400 billion. That was the upper bound for the number of stars within our galaxy. That's a 4 followed by 11 zeros, as notated there. The second set of numbers were those that resulted from this growth curve, from this exponential growth, where we doubled every successive iteration. So we had 1, 2, 4, 8, 16, 32, 64, and so on. Those numbers are written here, and they can be expressed as powers of 2. Remember, this was an exponential growth curve where 2 was the base, so we had the formula y equals 2 to the x, where x represents the level that we're on, or the iteration that we're looking at. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, and if we go up to 2 to the power of 10, that's 1024. So that figure 1024 on the right hand side represents 2 to the 10th power. If I look down to the row below to the equivalent position, I would have 2 to the 20th power, and that gives me 1,048,576. So it's just over 1 million. If I look down to the equivalent position in the third line, I would have 2 to the power of 30, which is now over 1 billion. If I look down to the equivalent position, in the fourth line I would have 2 to the power of 40, which gives me something which is just over 1 trillion. 1,99,511,627,776. Now that is way more than the number of stars that we've assumed, even at an upper limit. So we need to scale that back. And if we go back a little bit, what we'll find by several factors of 2 is that around 2 to the power of 38 will give us 274, almost 275 billion. That's enough, because we're not just looking at the individual terms in this escalating sequence. What we're actually doing is we're forming a series. That is, we're summing up all of the terms up to that current term. And when we do this with this sequence of numbers, what we'll find is that the value of the series is almost exactly twice the value of the number that we sum up to. So for example, if we sum the first 5 terms, 1, 2, 4, 8, 16, what we get is 31, which is almost exactly double 16. If we sum the first 6 terms, 1, 2, 4, 8, 16, 32, we get 63, which is almost exactly double 32. So by taking 2 to the 38th power, 275 billion, when we form the series, we sum all terms up to and including that term, we will have a number which is over 500 billion, which is more than the number of stars that we've assumed to be in our entire galaxy. Therefore, that's the total number of iterations we need at maximum to be able to populate or colonize every star system within the Milky Way. Now, let's do a little bit of maths. Each iteration represents a journey between 2 stars. Remember, we assumed that the distance between any 2 stars was more than what it really is. We assumed that it would be at most 100,000 light years, the diameter of the galaxy, and that it would be that for every 2 stars. Well, supposing we can travel at the speed of light, that means that distance takes 100,000 years. So every journey, every iteration will take 100,000 years, and there are 37 of these iterations in order to populate, to colonize every star system within the galaxy. So that's 37 times 100,000, which is 3.7 million years. Now, even if we assume that we can only travel at a fraction of the speed of light, say 10% of the speed of light, well, that means that distance each time will take 1 million years instead of 100,000. So it's 37 times 1 million, which becomes 37 million. Even if we assumed that we can only travel at 1% of the speed of light, then that journey would become 10 million years, and that would be 37 times 10 million, which would be 370 million years in order to colonize everything within our galaxy. And that is a vanishingly small fraction of the age of the galaxy. So the question is, if someone was to do this, easily it could be done within the time frame of the age of the galaxy. So why can't we see, best as we can detect, other life? Why haven't we been able to see it yet? I'm not drawing any conclusions, but I'm just pointing out the mathematics here that could be used to determine the solution to this. Here's a screenshot from Desmos of 3 curves, 1 exponential growth curve and 2 power function curves. The red curve is the exponential curve. This is y is equal to 2 to the x, so I've chosen the base of 2, which is a very low base. It's the lowest integer base where there could be growth. If I had chosen 3 or 4, 5 or 10, then this curve would be growing far more rapidly. But I'm going to demonstrate that even with 2 to the power of x grows so rapidly that it will outpace any power function. Now the other 2 curves, the green and the blue one is y is equal to x squared, which means for every corresponding horizontal value we square it. we multiply it by itself to get the corresponding vertical value. That's what that blue curve represents. And the green curve is x to the power of 10, which means for every corresponding horizontal value, we multiply it by itself 10 times to get the corresponding vertical value. So for example, if you look at 2 on the horizontal axis, for the green curve, we multiply 2 by itself 10 times. 2 to the power of 10 is 1024 to get the corresponding vertical value for that curve. That looks like it outpaces everything, but I'm going to demonstrate that the red curve, thanks to rapid growth, will outstrip either of these curves. In this slide here, I've compressed the x-axis, the horizontal axis, by a factor of 10. And in this third slide, I've compacted the x-axis again by a factor of 10. So those three curves look vertical there, from the origin going vertically up. Now I'm going to start compressing the vertical axis, the y-axis. In this first slide, we can begin to see some distinction between the three curves as I go up to 1000. In this slide, as we go up to 10,000, we see more of a spread between those three curves, with the blue curve being pushed out to the right. In this slide, with the axis going to 100,000, we can see the blue curve being pushed out further. This slide, going to 1 million, the blue curve is almost becoming flat. Here we are at 10 million, and it's almost exactly a flat line, whereas the red and the green are shooting off almost vertically. Here at this one, 10 to the 15, the blue curve is exactly flat at this scale. The red and the green are shooting off vertically, almost. Here at this scale, 10 to the 18, we've scaled out by a factor of 1000, and we notice at this point the red curve has overtaken the green curve in terms of rapid growth. Here we are by a factor of 1000 again, and the green curve is clearly being outstripped by the red curve. And if we go to the next slide, we can see that the green curve on this scale will almost soon be a flat line, whereas the red curve is shooting away what appears to be vertically. And at this final slide, the green curve is flat and the red curve is almost exactly vertical. That is rapid exponential growth on a large scale. Thanks for watching this video. I hope it's been of some use and given some food for thought. If you enjoyed it, please feel free to like and subscribe and have a look at the rest of the channel if it can be of use. Thank you.